With this lecture, we start discussing the global positioning system GPS, which has become recently a very important part of our lives. GPS really is an abbreviation for something rather long: Navigation, Satellite, Timing and Arranging Global Positioning System, Navstar GPS, or just plain GPS. It is a satellite-based navigation system which has excellent worldwide coverage and allows the user access to unusually accurate positioning and timing information. GPS has been described as the most significant development for safe and efficient navigation and surveillance of air and spacecraft since the introduction of radio navigation 50 years ago. It has had a widespread impact which continues to grow because its accuracy is increasing, it has global availability, and the cost is going down, as usual. The GPS program was formally initiated in 1973, and by 1995 the system was declared operational. There are several other systems in the works. Is a Russian one, GLONASS, not quite complete, and a European forthcoming system, the Galileo. Now, as far as the GPS is concerned, it consists of what's called segments or subsystems. There's a space or satellite system which broadcasts position and time signals as well as other messages. There's a user segment, that's the GPS receivers, which receive signal to determine position, time, and so on. And there's a ground control which updates information disseminated by each satellite, monitors satellite health, controls satellites, and so on, switches them in and out of the system as it might become necessary. There's a master station in Colorado Springs and several uploading stations and monitor stations spread around the world. There's a brief illustration here of the three segments: space, the satellites emitting in the range of 1 gigahertz, both navigation and status signals. Here's the receivers in the air, on ground, on water, and here are the control station. There's a master station and other stations that are used to upload information because not all satellites are in direct view of the master station. The GPS satellite constellation consists of 24 satellites at a certain inclination, altitude of about 20,000 kilometers, and the user anywhere on the globe can receive signals from at least 4, and we'll see why 4 is the minimum number based on an estimation problem, and up to 11 satellites. So that's how the constellation looks. Now, what is the GPS principle used for positioning? The basic principle of the GPS positioning is to calculate the distance between the user and each visible satellite by measuring the time a signal travels from the satellite to the user. The user's position, which is given by 3 coordinates, can be estimated from 4 such distances, accounting for an additional unknown, the receiver's clock offset, delta t, from the GPS system time. Since no clock is perfect and the times of propagation, even for about 20,000 kilometers, are very short, obviously there is need to estimate the local clock's offset from the GPS clock at the same time as the local location, local coordinates. We have an illustration of this, and this is called the pseudo-range positioning, because what is measured is a time difference, which is really the equivalent to a range, but because we don't have a perfect clock, is a pseudo-range. So the signal traveling time is determined by the time shift required for a match between the received code from the satellite and the receiver, which can replicate using start time information the same code. Each satellite will also broadcast its clock offset. It turns out even the satellites don't have perfect clocks, and those minor deviations matter. That's tau I, and this is relative to the GPS system time. So there are 4 unknowns to be determined. Once the satellite knows its clock offset, there is the receiver clock offset and the 3 coordinates of the receiver. So that's why 4 satellites is the minimum to have in sight. With more satellites, the positioning error due to the measurement errors can be reduced. Effectively, what's done is a least squares problem can be solved. And this is the figure that shows the code that is sent out, a sequence of pulses under the assumption of perfect satellite clocks but biased user clocks. We need 4 satellites, and we have the user bias from the system time, and these are to be matched with the received signal. And when they are matched, then we have the 4 delta t's. The range, or the pseudo range, is really the speed of flight c times the delta t1 plus the delta t cap t, which is the user bias from the system time. So this displacement in time is equivalent to a pseudo range. Will be the exact range if the local clock were perfect, but as I said, it has to be accounted for that the local clocks are not perfect. Now there can be another twist. Biased clock satellites can be accounted for by having the same expression but a minus here, the satellite clock bias, which is constantly monitored, uploaded from ground station and transmitted together with the pulses. Now the GPS signals consists of a carrier, a spread spectrum code of pseudo-random numbers, and a binary data message, and it includes quite a bit of information: the satellite's current position, the time the signal is sent, and the satellite's health information. And one of these is the satellite clock offset. There are 2 types of service at this point. In the future there might be more. That GPS provides a standard positioning service. There's a course acquisition code, the CA, course acquisition code for civilian use, and there's a precision positioning service, PPS. There's a precision code P code or Y code for military use. The P is unencrypted. There is another one classified W code, which generates the encrypted Y code to avoid spoofing, and more are in the works. Now each satellite broadcasts direct sequence spread spectrum signals on 2 carriers. This L1 on 1575.42 megahertz per 1.5 gigahertz, and this is the modulation. So the CA code, course acquisition code, will use this X, that's a plus or minus 1, at a frequency of about 1 megahertz, and the P code will be at a frequency of 10 megahertz here. So this is the carrier. D is the navigation data, which predicts the satellite's location and clock offset relative to the GPS system time. There is a secondary carrier, L2, at 1.2 gigahertz. That's for P code is required for this, And what it is used to is to estimate signal delay due to ionospheric and tropospheric refractions and multipath effects. It turns out that the speed of light is not constant, and light does not propagate in a straight line, and all these corrections become vital when we want to get the highest possible accuracy. And some more signals are in the works. Now, what are the observables? The basic equation for the GPS positioning are the pseudo-range equations. If we have n visible satellites, rho is the pseudo-range, r is the true range. This is the location of the satellite, cap x, y, z for satellite number I, subscripted by I. X, lowercase x, y, z are the coordinates of the user. And what we have here is that the pseudo-range is the range plus c delta t. This is the timing error, the receiver clock offset from the GPS time, plus noise. And while we use the same symbol as before, this noise is not really white, and that's one of the complexities of the GPS, that it is not white. So we have the pseudo range here, Ri plus C delta T, which is psi I plus an observation noise. Speed of light, there's a nominal speed that is used, and the measurement error. Now, what are the errors due to? The so-called selective availability, which consisted of dithering, introducing timing errors to reduce the accuracy, that has been done away with. The errors due to ionospheric and tropospheric refraction, they are there. Multipath effect, satellite position errors, even the satellites are not, their location is not known exactly, even though this is a fairly small component, and then receiver noise. So this dithering with the selective availability has been discontinued, so it doesn't matter anymore. Now, the pseudo-range measurements are based on determining the time shift, phase difference of the either CA or P codes, and measurements can be made also based on the phase and frequency shift. This gives a range, this gives a range rate. So what is called the delta pseudo range is really an integrated Doppler or carrier phase measurements, and these can now be also used to determine, to make velocity measurements for the receiver. So you can get position measurements, you can also get velocity measurements. So the GPS Doppler measurements measure the Doppler shift in carrier frequency due to the relative motion between the satellite and the user. So R dot is lambda delta F, where R dot is the range rate, lambda is the known wavelength of the carrier, and delta is the Doppler shift, that's the difference in the frequency between the receiver replicated and the received carriers. So it turns out if the receiver replicates the carrier, that's not exactly what is received by the receiver, because there will be a Doppler shift in the case of a relative velocity. This is the range rate, the rate of change of the true range. This is really the projection of the relative velocity vector along the line of sight direction. And these are called delta range measurements after integration. So we can measure the range rate counting the number of Doppler cycles over a short period is what yields the delta range. And one can do a longer term integration as well. So that is effectively a carrier phase measurement. You integrate frequency, you get phase. Now, the noisy carrier phase measurement, phase phi, is psi over lambda plus the ambiguity. There is a problem, there is an integer ambiguity in the code, because you can overlap another code rather than yours, so that's another problem that typically is handled at initialization. So this integer ambiguity appears because it is impossible to distinguish two carriers that differ in a phase within an integer cycle, and thus only fractional cycle phase difference is measurable. This determination is extremely important in utilizing carrier phase measurements. And the measurement error for the phase W sub phi is made up of time-correlated errors as well as white measurement noise. So overall, these measurements are corrupted not just by white noise. And special models are needed to handle these noises. It includes errors caused by refraction, satellite ephemeris, trajectory error, and receiver measurement noise.